Hi and welcome to Axiom Chemistry. In this video we're going to talk about solubility, and we're going to begin by thinking about the lab you've done which explored the solubility of sodium chloride in water. Here's my lab report, and here are my results, graph and conclusion. Now if you plotted a graph of your data, you should have got a curve, something a little bit like this. Here's a more accurate graph showing the solubility of sodium chloride in water between 0 and 80 degrees Celsius. And as you can clearly see, the data is in the shape of a curve. In fact, a graph like this is called a solubility curve, and different substances dissolved in different solvents will have different solubility curves. Let me show you some more examples. So this graph shows the solubility curve for sodium nitrate, copper sulfate and potassium chlorate all dissolved in water, and as you can see, they vary quite a bit. Now, the data used to produce these curves is not usually found by dissolving the substance in water in the way that we did in our lab. It's usually found by evaporating saturated solutions. We're not going to do this as an Axiom Chemistry lab, but I am going to show you a typical lab report from an investigation into just one data point on one graph. So here it is. The lab report, of course, starts with a title, and mine is Finding the Solubility of Sodium Chloride in Water by Evaporation. Next, we need a goal or a hypothesis, and I've written a goal, which reads to determine the amount of sodium chloride dissolved in a saturated solution. So that's what I'm trying to do. And to do that, I need a method. So first, the mass of a heat-proof beaker was measured. Saturated sodium chloride solution was added to the heat-proof beaker, and its temperature and mass recorded. The apparatus was set up as shown in the diagram. Okay, I should probably show you the diagram. Here is my heat-proof beaker, and in it I've got that saturated sodium chloride solution. The beaker is resting on top of what we call a tripod. Let me just sketch that for you. I'm going to show you a photograph in just a minute, but on top of the tripod sits a piece of thin metal gauze. And that's to stop the beaker falling through the tripod, because the tripods are usually shaped something like this. You can see that it's got 3 legs, hence the name tripod. But at the top you've got a gap, and so you need that piece of metal gauze to stop your beaker falling straight through. Okay, let's go back to our method. What next? The beaker was heated until all the water had evaporated. So let me just sketch that in the diagram. I'll show that it's being heated by just putting a sketch of a flame shape, and the piece of equipment that's used is called a Bunsen burner. Now, Bunsen burners, which are named after the German chemist Robert Bunsen, are gas burners which produce a single open gas flame. Let me show you a photograph of a typical one. It's used for heating, sterilization and combustion. The gas that's used is usually natural gas, mainly methane, but sometimes a liquefied petroleum gas like propane or butane is used. The temperature of the flame can be altered by changing the airflow into the burner, which is done by turning this little collar here, which has got a hole in it. You can see the hole kind of just round there in the collar. Okay, let's go back to the method. What next? Well, once the beaker had cooled, its mass was again recorded. So that's my method. Now let's turn to the results. So first, once the water had evaporated, the white salt crystals were observed in the beaker. The initial mass of the beaker was recorded, as was that initial temperature of the solution, the mass of the beaker with the solution in it, and then also the mass of the beaker and salt after evaporation. So that's when it had all cooled down again. So those were the results. We need to analyse these results though before we can draw any conclusions. So some analysis. What was the mass of the water which evaporated? Well, that was the mass of the beaker with the solution minus the mass of the beaker and salt after evaporation. And you can see that that was 100 grams. We also need to know the mass of the salt in the solution. Well, that's the mass of the beaker and salt after evaporation minus the initial mass of the beaker. And so you can see that's exactly 36 grams. And so now we can draw a conclusion. We can say that the solubility of sodium chloride in water at 27 degrees Celsius, because that was the temperature of the solution, is 36 grams per 100 grams of water. So it's a very simple conclusion from that data. If we go back to our graph, you can see that that data point would fall around about here, but it is just one data point on this curve. So in order to actually produce the curve, of course, you need to do that experiment many times. And so it's an awful lot of work to determine a solubility curve. Not just this one, but also, of course, all of these other ones. So these curves, which you can look at very quickly, are the fruit of a lot of work from someone else. So you might now be wondering why someone would bother to do all that work. Well, solubility curves have lots of uses. For instance, they're used in research to predict which substances will crystallize out first from a solution containing 2 or more different solutes. Okay, as ever, here is a summary of what we've discussed in this video. We've seen that graphs of solubility versus temperature are called solubility curves, and that solubility can be calculated by evaporation. If you need to write this down, I suggest you pause the video and do that now. Well done, and see you in the next video.